I am Liz Cruz, and this is the Chip to Chiller, How Liquid Cooling Connects the Modern Data Center. And I'm here today with Surjan Mutabdia from Vertiv, Rich Bonner from Excelsius, and Vlad Galibov from Omdia. And the reason that we wanted to pull this session together today is because liquid cooling is really at an inflection point where it's no longer an if, but a how. And it's funny because this is my 15th year at Data Center World, and it always serves as a great yardstick or measure for how technology is getting adopted. Over the years, as different, things have been the main theme, whether it was cloud or edge or prefab. The first year is always, what is it? Do we even need it? And so 3 years ago, that's what we talked about here when we were talking about liquid cooling. It's, do we even need this? How long will air last for us? Last year, it was a conversation about, is it single-phase direct-to-chip or two-phase direct-to-chip? And then this year, there's becoming a consensus that it's really two-phase direct-to-chip that we're going to need to move to in the long run. And I don't know if any of you made it to the University of Chicago's session 2 days ago, and he was talking about the different liquid cooling technologies he has in his data center. And when asked why did he choose two-phase, the answer was, I'm not doing single-phase for a 90-kilowatt rack. And we all know that's not even that crazy. A couple years from now, that'll be low density. So consensus forming around two-phase direct-to-chip. And then the second reason we really wanted to bring this together is because liquid cooling should not be talked about in a vacuum. There's dependencies, it's interconnected with so many other things. And when you're building a data center today, it's best case 4 years or average from site selection to rolling in a rack. And I asked Rich Miller yesterday kind of what his data points are in terms of lead times. In Virginia, it's up to 7 years. So what you're building for today, average 4 years, is not the chips you're seeing today. When you roll in a rack, it's not going to be what you know today and what you've had to build for up to this point. So we need to look ahead at the roadmap, and we need to understand where the chips are going to be, what does that mean for what kind of liquid cooling, and what does that liquid cooling demand in terms of the infrastructure. So that's why we have representatives here that are experts in chips, liquid cooling, and the broader infrastructure. So I'm going to ask you questions, and please introduce yourself upon your first question. But first, can I see a raise of hands for, it'd be good to understand how many of you are actively looking at liquid cooling for a near-term project defined 1 to 2 years from now? Awesome. Okay, great. So we can frame this as some educating, some really moving forward. So Vlad, I'll start with you, and you have your mic.
Right.
Can you give a kind of an overview of what you're seeing in terms of the different chip manufacturers' roadmaps?
Yes, so my name is Vlad Galibov. I used to work for Intel. Now I work for a technology research company called Omdia. And so when we think about the chip, what is the purpose for our being in the chip industry? It is really to pack more computing within a square millimeter of silicon. That really is our focus. Yesterday, one of the analysts in my team did a talk around how we're really pursuing this. We're now learning how to stack 16 high silicon chiplets so that we can make them denser. So this pursuit of putting more computing power, more memory on a square piece of silicon really is how the industry is moving forward. So it actually all starts with demand. So typically how we prepare the silicon roadmaps is we think about what are the applications of the future going to need. So we'll assess, for example, how much is the demand for memory, and then we'll decide how big the memory subsystem needs to be. So for example, for AI training applications or AI inference applications, we're seeing that memory, the DRAM memory, the cache memory, the high bandwidth memory that has to be in the computing device or on the chip, we need more of it, because then we can compute faster. If the GPUs in a cluster, a training cluster, can share memory, the high bandwidth memory that's on the chip, then they'll be able to do a better job. So now we're stacking it 16 high, so we're actually gluing, for lack of a better term, gluing together 16 chiplets, which creates a power problem. Simultaneously, we're adding more transistors on the computing side so that we can have more power on a square piece of silicon. So the chip roadmap it has no chance but to actually accelerate because we want to have bigger models. We want to use AI more. So that's kind of what we're seeing. Really, there's no limit to how much power chips can consume. Yesterday, my team gave a very good example. There is a 20 kilowatt chip out there, the Cerebras wafer scale engine. It's liquid cooled, and they had to make it, a custom cooling. It's not a mainstream chip. It's not like the NVIDIA ones, but as we know, these are all getting denser and denser from a computing and memory perspective.
Oh, wow. That's a very fun fact. I did not know that. So, Rich, I want you to talk about kind of what obviously that means for liquid cooling. But first, how many of you feel like you understand two-phase direct-to-chip really well? Or should Rich give a little overview of that? Raise your hand. Oh, yes, you would understand very well. OK, but it does seem, if you could give just a quick overview of two-phase.
Sure. Yeah, hi, I'm Rich Bonner, CTO of Excelsius. I have about 20 years experience doing various forms of two-phase cooling, from heat pipes, phase change materials, and of course pump two-phase for a variety of government, military, defense applications. Excited to be now part of the data center community, trying to bring some of those advanced technologies to this market. Direct-to-chip two-phase, I like to start by saying it looks a lot like direct-to-chip single-phase. If we were to walk by a rack of direct-to-chip two-phase, you probably wouldn't even see any difference at all. We use similar cold plates, manifolds, CDUs. Really, the difference is what happens inside the cold plates and inside the CDUs. So with two-phase direct-to-chip, you're going to basically be circulating a fluid that is near saturated conditions. And when you bring that fluid across your cold plate, the heat from the processor is going to cause that fluid to boil. And as you that fluid traverses the cold plate, you're going to take that liquid and convert it to almost nearly all vapor upon its exit. And then you'll send that vapor to a manifold, condense it somewhere, and then recirculate that fresh liquid back to the cold plate. So at the end of the day, what you do is you essentially get a system that is serviceable, fits the standard architectures of any kind of liquid cooling system, but you get the benefit of that boiling process, benefit of that condensation process from a performance standpoint.
That's great. Thank you so much. And in terms of kind of the power densities that he was talking about, or the power levels, why is two-phase kind of needed for that?
Sure. I mean, I start by thinking about air cooling, and basically you saw the roadmaps almost trend towards a certain level where processors weren't going to higher heat fluxes or higher TDPs because there was just that demand for people who wanted to stay with air. This AI application has pushed the processor demand, the performance demand, where they need faster processors, they're going to generate more heat, so you go to the next best technology for removing that heat. In this case, I think single-phase direct-to-chip was most ready, so that's where it went. But now they're going to even higher densities. So if you want to remove power now at an even higher density, the only way to keep the silicon at the same temperature is to use a technology that has lower thermal resistance and allows you to maintain that same silicon temperature as you were at those lower densities. And like I sort of alluded to before, two-phase cooling has several inherent benefits. I think the one I like to teach first is that you're basically trying to stir the fluid near the wall, right? That's really critical to any heat transfer process. The way you do it with single-phase fluid is you pump more water fluid, you get more turbulence, you get thinner boundary layers. With boiling, it happens at the wall, right? So that you get this beautiful creation of turbulence as you're basically letting the vapor expand near the wall. You're essentially stirring the fluid exactly where you want to stir it. And that's what really gives you the magical kind of properties you get with two-phase compared to single-phase. And there's other benefits too. I think we'll probably get through it throughout the panel, but that's the one where I start with. So.
Perfect, thanks. So Surgeon, if you wouldn't mind also introducing yourself, but so when we have, and we've been working more closely together, when we have a company that wants to adopt any liquid cooling technology, there's many upstream things that must occur beyond the rack to final heat rejection. So what are you kind of seeing and what are you advising in terms on how to implement liquid cooling beyond the rack to final heat rejection?
Hello, my name is Sergio Mutabgia. I'm leading the innovation, liquid cooling technologies and emerging technologies in Vertiv, and working, of course, with all of our physical infrastructure counterparts in Vertiv to enable you to have answers that you're gonna need for the future. So if you notice anything from this Mr. Wonderful presentation, first thing I noticed is 7 gigawatts, but 5.6 gigawatts is IT in that Wonder Valley. So it's kind of terrible PUE. So that's my engineering mind. I need to figure out how much power they're using for this gas stuff. And the second one that's very important that he said, the chips, the IT guys, racks, they're gonna bring new stuff every 2 years and pushing towards 1 year in the future. So you as a data center operator need to figure out what the hell do I do with this stuff. So, so number one, the philosophy of data center design that's changing, that has changed, is that NVIDIA and Intel and AMD and many IT guys didn't really talk to physical infrastructure guys before. There was a fine line, right? They lived their life, we lived their life, we gave them fans, we cooled the stuff, and they loved it. Now, the first conversation you need to have is what's coming out of those racks. What do you need to provide to those racks? Is it 45 degrees seawater? Is it refrigerant? What it is that you need to provide to these racks. So the data center design, yes, you need to have 7 gigawatts power, you need to figure out the land, all that stuff. But you as a data center designer, operator, need to ask the question of your IT people first, is what do I need to provide on the chip level, on the server level, on the rack level, and then design out towards the atmosphere or heat reuse or chiller, whatever you want to call it. So that is kind of right. What we are doing in Vertiv is ensuring that you can do that today with the direct-to-chip single phase, but also put your designs in place that's going to enable you to do refrigerant or whatever else that we're going to need to cool these racks moving forward. So that is the, if I can, you know, on your last day of this beautiful conference, get you anything out of leaving today is you need to start your design from the rack first and what's needed in those servers, and then we're going to figure out the rest of the stuff easy. Because our number one job is to protect these chips, and then, of course, number two, how do I design my data center that's super efficient, low OpEx, all those things that comes next.
Of course.
So I really like this idea of you need to remind yourself what you're doing, what's the density of the rack, what does the chip need for the cooling. But as you do that, what's going to happen is you're going to realize this is difficult, right? So it's very easy to think, why am I wasting my time doing this? I could have a much, kind of simpler life, and I can just not do this, right? So when that kind of fear and the worry and the over complexity of it, because it is very complex, comes in, I think you need to remember why you're doing it, right? One of the best things that Kevin O'Leary said on stage this morning is the return on investment that they're seeing from using AI. And ultimately, we don't run a data center just for fun, right? You're not buying multi-million, multi-billion-dollar servers just for fun. So I think when the going gets tough, probably the best thing to do is remember that there is actually a benefit that is at the end, of the struggle.
That's a good point. Yeah, I think it's funny to realize nobody wants to do this. This is not a fun activity for anybody. So I'm going to actually pause, and since we have such a good turnout, turn it around and ask. Everyone's in a different place on their journey. So are there any questions from the audience? We'd love for this to be more interactive. Does anyone have any questions? Yes.
So question, as you look at two-phase, what is the type of chemistry or materials that work best there? PG25 has a lower heat capacity than pure water, but both of them kind of operate fairly well there. Where do you see this going for most efficient two-phase cooling systems?
Yeah, most two-phase systems are not going to use they're not going to use the same single-phase fluids that you're currently using. Actually, most two-phase systems, actually in our systems, all of our competitors are using some form of refrigerant or dielectric-based fluids. Our fluids that we're using are, similar to fluids that are used in chillers and those types of applications, vapor compression systems. So, if you follow, we're using like Honeywell Solstice products. I think Chemours has some fluids. They're widely available. well, I'll also say this, the fluids we're talking about are, they're not bespoke for direct-to-chip two-phase cooling. I think that's important to note, only as it relates to worldwide availability. That might not be true of some two-phase immersion fluids that are a little bit more niche and may not even pass certain regulations. I think there's challenges there. But in direct-to-chip two-phase, we're using refrigerant fluids, but at the same time, even though they're refrigerants, we're not using compressors. We are pumping our solution, so we still have the same efficiencies, actually lower pumping power than you're going to get with single-phase based solutions. But yeah, does that answer your question? No. Okay, good.
Does the temperature of heat rejection go up for a two-phase solution versus a single phase?
Thank you for that question. Everything we are working on the two-phase, actually our goal is to save facility water temperature at least 10 or 20 degrees C. So that is the beauty actually of the direct-to-chip two-phase technology, that all of the CDUs, or coolant distribution units, are rated at a 50 degrees C facility water temperature. So when you listen to NVIDIA, right, and maybe if you listen to keynote, even on the single phase, they do want to run 40 degrees C to the chip. However, as an industry, a lot of hyperscalers, for example, are designing much lower than that because they're afraid what's coming next. Will the single phase at 45 C be able to cool the chips of the future? So there is a big, discussion, dynamic discussion in the industry, what water temperature means for the single phase. So a lot of our customers are designing at 30 C. 30 C to the chip means 25 from the chiller. So that is the beauty actually of two-phase, and benefit over single phase is that everything we are doing, we can cool the same as single phase at 50 degrees C facility water temperature.
And that's a great answer. I want to add this to it. So he made a good point about two-phase being 10 to 20 degrees C better than single phase. And that can allow you to run your facility water hotter if you'd like. But there's other things you can do with that performance too. I mean, you'll see some customers will still choose to keep their facility water at 15, 20 degrees Celsius and simply, push higher power densities, maybe even overclock certain processors. But it all starts with that improved performance. You take that 10 to 20 degrees performance, you choose what you do with it. You could save energy, you could push performance, you can do a lot of things.
Yeah, oh, go ahead. It's Vlad's job. Yeah.
So, so interestingly enough, my team and I just updated our forecast. We updated it. Why just now? Because we were at GTC and we got a glimpse at the NVIDIA roadmap. Very often as analysts, if we're told under NDA what the roadmap is, we can't bake it into our forecast, but now we know officially. So for us, that turning point is once you see the 2027 architecture that NVIDIA has. It is the chip that will already launch in 26 is a very high power chip. But the ambition is then to take that same chip that will launch in 26 and put a huge number of them in the same rack. At that point, you are running into a lot of constraints. So you are looking for maximum efficiency gains in the cooling technology so that you can actually put more chips in the rack. So the cooling lead in my team, Shen Wang, is sitting here on the second row, and we basically believe that 27 is that kind of turning point where you see a big increase. There's going to be deployments before that, don't get me wrong, but they would be in parts to learn, to start to use it. They might not be micro scale, but they would be smaller scale. And then from 27, we really think that to be able to actually achieve the maximum computing performance and to put as many chips in a cluster as NVIDIA suggests, it's probably going to benefit you to have efficient cooling.
Just add quickly to that, right? We have internal joke in Vertiv. Direct-to-chip single phase is just a pump and a heat exchanger, right? So it's pretty simple. But it's not about, right, let's even say cold plates and CDUs and cooling systems are ready, it's also enabling our ecosystem of partners to make sure our customers can get all this stuff quickly and easily, refrigerants, QDs, hoses, everything. So that's why, right, direct-to-chip single phase is taking off right now, because there is a whole ecosystem of partners that's now going at it, and you can buy all these pieces. So that's why it's important for you to understand that we are not just enabling, right, cold plates and coolant distribution units and heat rejection. We are enabling whole ecosystem that's needed to make this technology mass ready.
Can I add one thing?
Of course.
Sorry, one thing that I didn't mention earlier when we were talking about the silicon roadmap is one of the things that's very obvious to us now is actually achieving some of the miniaturization that we have utilized in the silicon roadmap that has actually enabled for us to do more computing over the last 7 decades. That is getting harder because now we're really designing and we're etching transistors at the atomic level. So then as a result, the only thing we can do is we have to start stacking silicon. So that really is having an incredible impact on the power. So to the gentleman that asked, when does it become mainstream? An ascent will start in 27. But what's going to happen is in 2018, 2019, 2030, the power of the chips, there's no way that it won't continue to grow, even at the square millimeter level, just because now it's not one layer of silicon, we're starting to have multi-layer of silicon. So you're having, a doubling effect potentially of power of chips. And I'm not saying that to scare you. I think that is solvable, but it's because we're facing the laws of physics when it comes to transistor manufacturing.
Yes, sir.
Yeah, a significant amount is
Do you want to
compatible.
just, in case, he asked how much of the infrastructure that's compatible with single phase will be compatible with two phase?
You're saying the parts of the cooling system itself? Yeah, you're right. So, like I think I said this in the introduction. If you were to walk by and look at a direct-to-chip two-phase side by side with direct-to-chip single-phase, they would look very similar. And as a result, most of those components can be used as well. We're going to have manifolds, pumps, the metal parts, even brazed plate heat exchangers. Those parts are highly compatible, almost the same. But certainly there's, again, maybe connecting the other question about fluids. When you change fluids, you also have to change usually the other elastomers that are going to be in contact with that fluid. So within certain parts, like the quick disconnects, the pumps where there's seals, there's some things that have to change, some designs that have to change. But we're talking to the same suppliers, right, of those components. And I think because of that, when we go to scale direct-to-chip two-phase, when we get those adoptions, I think there's going to be a lot to be leveraged there.
So the first generation direct-to-chip two-phase units will be water on the primary, right? So we are putting all kinds of water loops in the data center now. So you're going to take your single-phase CDU out, plug that water into two-phase, and then your loop is going to just be from CDU to the rack, so simplify that part. And then if the future, right, of course, a lot of talk about refrigerants. If you're in that world, you can imagine, right, all the things and discussions of that end. But then in the future, you would, if you prefer, right, or your data center is ready for it, you don't have water, you're in hot climates, it can be a refrigerant on the primary, so you're going to have a refrigerant closed loop system all the way to the rack.
I mean, and that's a great point, right? Sometimes we get questions from people building new data centers like, oh, what do we have to do to future-proof to make sure our new facility water system is compatible with two-phase in the future? Nothing, right? You're basically going to be pumping the same fluids at the same pressure drops through our heat exchangers and valves and everything else. You have to change nothing. All you have to do is change the CDU or cold plates that go in the rack, in the white space, but that whole other part of the facility is exactly the same.
Do you mind if I add something?
Go ahead.
So because retrofit is a very interesting question, right? So the biggest part of the cost equation for liquid cooling when we look at the different components. Actually, today, cold plates are a very large part of it because, there's a lot of copper, they're very expensive, they're very heavy. Copper is expensive. So that is already a part of your server. So what are you really retrofitting? So you would not change from 1 to 2 phase on a server you've already purchased. No one would do that. It's just that you will purchase a new server that's denser, it has higher power components, so it would already be fitted with the cold plate that's compatible with 2 phase. And then, yes, you might need to plug the CDU. The CDU is not as expensive as it sounds, especially as a proportion of the investment of your cluster. The hardest thing is actually the infrastructure that's, underneath the raised floor and, kind of getting everything set up. So that is retrofittable. And I think it's good to break the problem into cost. The highest cost, which is the cold plates, is already retrofitted by design because it's a part of the new server.
That's, I think, bringing up retrofit at the server level, but then also retrofitting at the data center level. There's many, many, many data centers out there today that don't have facility water loops. So what is the option for those facilities, and is there a refrigerant to air option?
Yeah, that's something we're working on. I think, I'm obviously familiar with Excelsius's roadmap and see what's coming. From just technically speaking, there's no reason you can't have a 2-phase CDU and then condense your refrigerant directly in a radiator right next to it, similar to how any of the liquid to air type solutions would work. And we are working on that. So I love actually the idea of that solution because we have a lot of customers who really don't want to have water in their data system still. Obviously, a lot of people are past that, but there's some pretty conservative markets where that's still a big issue. Going refrigerant to air prevents any kind of water in your data center, which is a unique advantage in itself. Probably at a larger scale, I think having that refrigerant to air just allows you to more quickly tap into all the brownfield sites that are already there that are still years away from getting their facility upgrade.
Yeah, it does not matter, right? It's important. It does not matter how your data center look today. There are solutions out there that can easily transform it to the direct-to-chip capability. So I just want to make sure that's important note to take also, because a lot of people think, right, even direct-to-chip single-phase means chiller. Well, maybe not. If you have a condenser on the roof or something, you can have indoor split chillers or something that's going to give you water loop where you need it. So again, very important, regardless of what you have today in your data center, assuming you have enough power, you can transform it into direct-to-chip facility easily.
Yes, sir.
Went to the ARPA-E Cooler Chips presentation, and NVIDIA came up with this idea of like each tray having immersion and direct-to-chip in it. So how realistic do you think that is?
It's realistic. I mean, from a functionality, I'm aware. I mean, I'll just maybe talk about that technology so everyone else can hear it. I know NVIDIA has a government-funded research program through ARPA-E, so it's future-looking. But what they're trying to do is do direct-to-chip 2-phase, but also have kind of an oil bath, basically a mini immersion on each tray to take off all the extra heat that would normally still be removed by air. So basically that oil bath removes heat off the memory modules, smaller components, hard drives, etc. And the interesting part about that is now you need no air going through the data center. Basically, you can physically, through liquid, remove 100% of the heat. How realistic is it? I think technically they're making good progress. I don't see any reason why it wouldn't work. I think from a market adoption standpoint, I always have this, we see the challenges with direct-to-chip 2-phase adoption. We also see challenges in parallel with immersion. I think getting two challenging technologies to be adopted at the same time is challenging, right, for sure. Probably pretty risky, but I will say that with the total power of the racks going where it's going, with total dissipated power on sockets going where it's going, I wouldn't be surprised if 5 or 6 years those types of solutions are taken more and more seriously.
Yeah, just to add to that, Vertiv is part of that project, so we're very familiar with it. But again, it's going back to the point that I made in the beginning. What are we cooling? Today, direct-to-chip cold plates are popular because we are cooling GPUs. But what's going to happen when we add the memory and the power supply and the switching, and they're going to need to be cold? Are we going to have a cold plate, the 7 cold plates around the server, or are we going to immerse it all because everything needs to be cooled? So that's where, we are at the beginning of this journey of innovation cycle liquid cooling, and hybrids might be the answer for all of it in the future. We already seen racks that are fully liquid cooled as a concepts, things like that. So it's really, again, up to IT guys and how they're going to design their servers, and we're going to figure out the best solution to cool those.
Do you want to add something, Vlad?
Yeah, I do. So, Drew, I think, great question, by the way. So the thing is, some of the, let's call them the proto designs or the beta designs of this idea, some of the practicality of how you maintain the equipment isn't there, to be honest. How Shen and I see this, how do you adopt it? How do you, because there is merit to this idea. You actually have to have the full system design so that this makes sense. So for example, how do you improve serviceability? Maybe the size of the server needs to change. Maybe the topology of the rack needs to change. How the components fit together might need to change. So there are ways to make even something like this highly serviceable and works, but you're actually designing with the cooling in mind. So it's like, it requires a lot of collaboration on the design. At the moment, the industry doesn't really collaborate as much, between chip designer, server designer, cooling designer. So I think that's what's going to take. You could have, let's call them cartridges that are hot swappable and they are fully immersed in liquid. That's possible. Both the new Meta and the new NVIDIA design utilizes something like this. It actually looks like one of the old Cray supercomputers from back in the day. Well, they still have them, so maybe I shouldn't use the word back in the day. But you know what I mean? It requires a lot of engineering. So at the moment, that collaboration in the industry realistically doesn't exist. That's why one of the reasons, NVIDIA's project is a research project today. Research projects are great, but at the end of the day, if you want to have a data center live in 2027, you want to be designing it now with the technology that's available now, working with a designer of server that already has a platform now. So I think how realistic it is for a platform like this to be on the market before 2030, to be honest, it's not very realistic.
Good insight. Yes, sir.
So when the power of the chip doubles, does the power or the heat from all of the other pieces in the server roughly double? In other words, do they grow at the same percentage of the heat of the chip, or is there a difference?
I would say roughly yes, right? I mean, when we talk about rules of thumbs for cooling racks, usually right now you consider that about 80%, maybe 80 to 90% of the power goes through the high power components and needs to be cooled by your direct-to-chip system, whether it's single phase or two phase. And we've kind of seen that scale as we've gone from 40 kilowatt racks all the way up to 250 kilowatt racks, which is interesting, right? Because 5 years ago, a 40 kilowatt air-cooled rack was state-of-the-art for air. And now even as we go to 250 kilowatt racks, you run that number, you're talking about almost 50 kilowatts of air cooling. So like when you're designing racks at those powers, you're basically solving a state-of-the-art liquid cooling problem and a state-of-the-art air cooling problem at the same time. But it just gives you some evidence of the challenges.
Yeah, I think somebody, Bill, or some presenters flashed that, cooling was taking, 40-30% of the power in overall data center before. So today, that's what, I'm flashing numbers, some numbers, guys, so I apologize. But liquid cooling parts are using 1 to 2% of the power they cool. So that is kind of what liquid cooling is bringing on that PUE efficiency power side. They're gonna need a bunch of power to power chips, but to cool them, we're gonna just use 1 to 2% of that overall power in the future.
Yes.
I'm not sure, Bob, we answered your question, so I'm actually going to add something. So it actually depends on, are you changing the ratios? Does the application requirement change? If you're starting to run a new application that might need more memory, you might actually start to have more power, higher capacity memory modules. That's one of the reasons why the correlation between memory and compute subsystem within the NVIDIA GPU changed several times in a row. They started stacking more memory because they realized the application is memory intensive. That's why the 20 kilowatt chip from Cerebras did not get adopted broadly. It did not have enough memory to run some of the large training models. So in essence, as the software ecosystem changes and you're seeing what your application needs to run faster, you might decide to have more or higher performance networking cards. You might decide to have more memory. You might decide that you need more compute cores. That can change the power draw on that. So it is possible that as your application changes, your compute doubles in power, but your memory quadruples or quintuples in power. That is possible. That is based on the requirement of the application. It's not just about fabrication, because you might just decide to put more of it in the system.
Good. Okay, yes, back there.
Yeah, with especially now you're talking about stacking silicone and when using cold plates, that's coupled to the top. You're taking heat off the top. What's going on the bottom of the chip? Is there a lot of heat going down the bottom of the chip into the socket, or is that not a problem? Cold plates.
Well, let me answer that. I'll take it. Okay, sure. So heat is going to leak out through the bottom, right? And it's like heat doesn't necessarily care where it goes. So if you're putting a cold plate on the top of the chip and your chip has a low thermal resistance path to get you to that cold plate, the majority of the heat's going to go into the cold plate. But there will always be some heat that will sort of leak through, and that's part of the heat that is going to contribute to what needs to be cooled by air, right? So if 99% of the heat from that chip is going into the cold plate, you still have maybe 1% that goes into air, and that has to be addressed by the facility or some other air cooling solution. But it's an interesting question. I think, especially when it comes, if you're familiar with the HBM cooling challenges, there's a very large thermal resistance in that HBM stack. It's almost like no matter how well you cool the surface of the HBM, it's still going to get hot just because it can't get heat out of itself. So one of the only ways to address that, one potential way may be to try to cool it from the other side, just to get heat kind of cooling from the top and bottom part so that the center of the HBM stays at a more nominal temperature. So people are going to think about that.
Yeah, I'm going to actually quote my dear colleague next to me, but so everybody likes to think about these simple terms, right? 500 watts per centimeter squared, 200, but chip has power map, heat map, that has peaks and valleys, and right, the heat flux. And that's why, right, when you start putting optics and memory and all these things together, they have different thermal performance and thermal limit needs. And that is one thing about single phase, right, is the water comes in, water heats up, and if it hits some heat flux hotspot in the first hit, that's where it's going to start losing its power. The direct chip two-phase, the beauty of it is uniformity of the cooling of the whole chip. So that is important to understand. Chips are not just watts per centimeter squared. They are the whole heat flux maps of hot spots, cooler spots, and that's where the two-phase doesn't really care about it. We're going to cool all of it uniformly across the chip.
Good point. Did you want to add something? No?
Yeah, it's a great point. Yeah, but we'll take another question. But
Oh,
it's good.
go ahead.
I was wondering if you talk a little bit about the potential difficulties or differences in maintenance or operations, single phase or two-phase.
Two-phase, my first comment will just be on the fluid itself. So the nice thing about these refrigerants that were brought up before, the same refrigerants you're using in your household, HVAC system. And as we know, nobody's replacing the refrigerants every 3 months, 6 months, whatnot. And the reason is really those refrigerants are non-corrosive, non-reactive. They don't facilitate biogrowth. So at the end of the day, with a direct-to-chip two-phase system, you're going to have much less fluid maintenance than you would with single-phase.
Yeah, so you got on my third, right? I have always everything I speak in threes, so top three benefits over two-phase versus single-phase. Better cooling of the chips due to heat flux, higher facility water temperatures, and number three is no water treatment needed. No sampling of the water, what is bacteria, what the hell is my chemical engineer saying? Yeah, you might have to top off refrigerant depending how many times you take the server in and out, but that is actually a huge benefit of two-phase versus single-phase. No water treatment, no sampling of the regular basis that we're going to have to do on single-phase today.
Can I add something? So as you plan in practice, right, running your data center, or maybe I should say, if I was you and I was running your data center and I'm making, kind of this crazy investment into these multi-billion-dollar servers, well, if your cluster is really big, let's say multi-million because maybe your cluster is smaller, what I would be thinking is cooling is a fraction of my cost, but it's so important, right? That the operations of that is so important. I would probably be buying a maintenance servicing contract. I'll be buying a monitoring servicing contract because it's serviceable, it's easy, but it's also critical. And the return on that service contract investment is probably going to be immense if your compute never goes down and you're able to actually deliver the return on investment on running the AI application.
Yes, sir.
I have a question regarding technician training. So do you expect the standard HVAC technician to service this equipment?
So I can comment on how we're designing our system. We're designing our system so that you don't need an HVAC certified technician. So whether it's servicing a pump or servicing even our instruments, everything's on quick disconnects. So for instance, we have pressure transducers that are critical to our control system. We can swap out a pressure transducer simply by pulling it off and putting another one on. There's no need for a recovery tank. There's no need for any of the types of activities that you would need to have a certified HVAC person. The only time you would need someone certified would probably be during the initial commissioning of that system.
Good question. Yes.
My first question would be, you talked about, I think you talked about having a facility refrigerant loop. Right now there seems to be kind of mistrust from the IT side to manage the water, and that's why they have CDU, I think. Is there going to be a higher level of trust from the IT equipment manufacturer to accept refrigerant that's being managed by the facility?
Nobody in IT world wanted water anywhere close to the racks, right? 2 years ago. Now it's regular thing. We love it, right? Nobody is worried about leaks. Same as refrigerants. It's going to be process. It's going to be understanding. But I think IT guys, arguably, maybe would we even be okay even more with refrigerants because they don't hurt servers, right? There's of course the regulation parts, standard parts, safety parts, all those things. But refrigerants probably would be, in my mind, even more welcome by IT guys than water because of the leak possibility of leaks.
These are great questions. Yes, Matt, did you have?
Yeah, just to follow up, because we keep on talking about refrigerants. So if you're doing two-phase, you want that material to be volatile. There's two ways to make things volatile. You get lower molecular weight, or you fluorinate it. There's a lot of activity out in the world talking about what happens when you fluorinate materials with low molecular weight. Do we need to not only talk to the folks in this room about the use of these two-phase materials, but what should we be doing talking to the community about the need for these lower molecular weight refrigerants that potentially have concerns?
I can maybe give it to Rich. I'll just quickly make a quick comment. That's going back to ecosystem. We are working closely with the refrigerant solution, right, mixers, and say, okay, we need low GWP refrigerants. We understand we need to fit all the regulations. So we are definitely working with them on that side.
And right now, these refrigerants that we have are the best ones that we have. I know the fluid manufacturers are doing their best to come up with fluids that meet all the demands of the data center market, whether it's flammability, fluorination, pressure, performance, et cetera. And nobody wants to use a fluid that's going to cause any harm to the environment or human health, right? But at the same time, I think the fluids we're talking about using here are fourth generation refrigerants, lowest GWP available. I'm a chemical engineer, but I'm not a bio type person. But I have read some of the articles myself on what's been done and published, and the ones that are cited by most of the agencies. And it seems to me like the health concerns are, I don't have health concerns. Basically, based on what the experts say and how I read it, I don't see any health concerns based on the amount of refrigerants, what they break down into, understanding how the refrigerants we're talking about using, how they in particular break down. I don't think it's going to be an issue. And I think that when calmer heads prevail, I think we'll be able to use the refrigerants we're using for a long time. And actually, all the refrigerants we're already using, even on the most stringent European regulations, aren't targeted to be banned in the next 5-10 years. They're not even on that roadmap. That being said, I think everybody would love a non-PFAS solution that hit all the other performance and flammability and safety requirements. And I think those vendors know that, and they're working on that. So it's something that's being addressed.
Rich, can you do a comparison of, just for the audience in case some people are not familiar, of how much fluid is necessary for a two-phase direct-to-chip versus a two-phase immersion tank? Because I feel like a ratio would be helpful.
I think we've looked at this. I think it's usually on the order of 30-to-1 is usually what we've seen. Yeah, so it's a lot less. Yeah.
That's a good point, Vlad. We have, I think, 3 more minutes. Yes, 3 more minutes. Any other questions? Yes, sir.
Sorry for so many. You threw out that cooling costs a lot less than the IT equipment. Could you throw a number at what you think is a reasonable percentage? So I can throw it in owner. He said the cooling costs too much. And I say it's only 3%.
You want to answer?
I can look at the numbers. I can figure, but I mean, you talk about $1 million racks, right? So I don't know how do we compare it. And the single phase, where are we? I can give you like how many watts per dollars. I'll check with, but I don't think that's. I think cooling is absolutely not shouldn't be part of cooling costs. Shouldn't be part of the discussion based on what they're charging for the IT racks.
So I need to check with the numbers, but the investment in total data center capex, because the thing is, it's not just about the compute versus the cooling. You have everything else. It's over $20 per watt at the moment because there's just so much. The price of, basically is because NVIDIA's prices are really high. Let's just say it as it is. And then the cost for the liquid cooling, I believe it's less than $1 per watt. I think it's close to $1 per watt, but I believe it's less than $1 per watt. So you have 1-to-20 ratio.
Very helpful. Yes. This has been a delightful audience. So many great questions. I super appreciate it. If you have any additional ones, I think we have a few minutes before the next panel, so feel free to come up and talk. Is there anything else that you guys wanted to add? Farewell? That's it?
Thank you.
Cheers.
Thank you.
Thanks.
Thank you.